Today we will unleash the power of AI in energy consumption prediction. Such practical problems like balancing electric grids and demand-side management require precise prediction of energy demand, and they are not possible without data, machine learning, and artificial intelligence. In practice, energy consumption may depend on different parameters and features related to energy market, time, weather, human behavior, and many others. Proper choice of the model, data preprocessing, and feature engineering ensures high accuracy and resolution of consumption prediction, resulting in improved performance and high reliability of electric grids. In this presentation, we will discuss one of important applications of AI and machine learning, prediction of energy consumption. First, we will talk about balancing the grid, both on large scale and in smaller smart grids. Demand-side management will be considered in the next section. We will see the role of AI in prediction of energy consumption. We will discuss suitable structures of artificial neural networks, choice of suitable sampling time, and necessary data preprocessing. Finally, it's important to talk about the main factors influencing the accuracy. Balancing electric grid is an example of application in which we need to predict energy consumption. The problem can be considered on different scales. On the large scale, a country or a region, we can predict aggregated consumption of all assets in a large grid. Practice shows that up to 98–99% accuracy can be achieved in case of a large number of aggregated consumers. In case of smaller smart grids, in some cases isolated or so-called islanded grid, the main problem is a large number of renewable energy sources. Another highly important example is demand-side management, a technology for controlling and optimizing energy demand on the consumer side. Optimal planning of the most energy-efficient consumption requires prediction of the demand 24 hours ahead. As an example, consumption in commercial and residential buildings can be considered, but the level of complexity of these tasks is very different. In large commercial buildings like shopping malls, hotels, office buildings, consumption can be predicted with high accuracy, taking into account important features like outdoor weather conditions and weather forecast, technical conditions of different systems, occupancy level, historical consumption data, calendar of holidays, and so on. In case of residential buildings, the problem gets one step more complex because it's practically almost impossible to predict consumption of each residential unit, private house or an apartment. Behavior of each individual cannot be predicted. That is why energy consumption has to be predicted in an aggregated way for a group of residential units. The main technique that is used for prediction of energy consumption is artificial neural network. It can be trained on a set of historical data. It's highly important to take into account that we are dealing with a dynamic process. Thus, static models are not suitable for this type of tasks. It's important to utilize dynamic models. In fact, applying AI techniques to a prediction task is the very last stage of the process. The main success depends first of all on data preprocessing and correct technical formulation of the task for a machine learning tool. In order to choose the proper number of inputs of the model used for prediction, at the first step we need to perform so-called feature engineering. The main factors influencing the accuracy of the model are related to quality of data, its preprocessing, and feature engineering. First of all, the features that correlate with the predicted value have to be chosen very carefully. It's important to pay special attention to the sample time and dynamical order of the model. We must use only data that can be properly measured. Please note that it means not only accurately measured physical values, but also keeping precise sample intervals of measurements. Try to avoid missing data. Remember that you need sufficient amount of data. For example, don't expect to make some reasonable predictions for the next day if you have only some days of data. Usually, you need at least some months, better several years of measured observations. At the end of each unit, you will find several questions to test your knowledge. Here is one of the questions. In what case we can achieve more precise consumption prediction in the grids? The answer lies within the materials covered in this unit.